Okay, everybody, welcome back on your Monday morning. Well, Monday afternoon almost. Yeah, but it's still Monday, so it doesn't really count. I mean, it still doesn't make anything better. Hello, we're going to start class. All right, so we're going to finish lecture number 2, move on to lecture number 3. Lecture number 3 is all on processes, and then at the end of today's lecture, I'm going to go over assignment number 1. And some people are freaking out already. They're going, oh my god, I don't have any programming experience, or they're doing something like that, and they're going, how am I supposed to do it? I will explain how you're going to do it. You're not going to be, for those people who have the programming skill, I highly recommend that you implement it in C or C++, hopefully C perhaps, because it'll be easier for you. We have UNIX access here as well. I don't have your accounts yet. Don't have the login information. Give me a week. I'll have that for you. The assignment technically is not going to be late until August 23rd. So we still have some time on it. Not to hurry, not to panic. So I'll have a UNIX login accounts for you because you'll need to use a UNIX system for it. And I'm going to talk about UNIX today and processes and how the assignment's going to work and stuff like that. If you have programming skill in C and you're a programmer, then do the assignment as it says. If you don't, then you're going to do like a pseudocode implementation. And I'm going to tell you what the pseudocode means in a few minutes, but at the end of today's lecture when I go over the assignment. I still want you to write the assignment. But it doesn't matter if it doesn't compile and if it's not in the C language. You may also do it in another language. If you know another language like Java as an example, some of you are in my Java programming course. If you like Java, you're going to have to change the assignment description a little bit in order to make it work in Java, but you can sort of mimic the same thing from a command prompt, from a shell. You're writing a shell, by the way, and the shell is going to have you use threads. It's going to be impossible to do in a Windows programming language because Windows doesn't support threads. So you're going to need access to a server if you're going to do it in C. If you have a MacBook, you're in great shape. You can use it. You can write it in C. If you have a MacBook, go to the Apple Store, download Xcode, and then in Xcode, here, let me just show you this real quick while I'm here. If you open up Xcode, download the C command line tools, and then you can type in GCC from a command prompt, and you have a Linux box for you. As an example here, if I go into the preferences, I opened up Xcode, going into preferences, and if I go, it's actually already on here, in the downloads button, I can see, let's see, command line tools right here. Actually, I need to install mine. I upgraded my Xcode. I haven't installed the newer version of it yet. But if you click on, what I did was I went into Xcode, hit Preferences from the Xcode menu for you Mac people. On the tabs up here, you want to click on the Download tabs on the top of the screen. And then make sure I was on documentation, but looks like I'm partially installed some documentation last time I was here. But click on Components. What you want is Command Line Tools. If you click on Command Line Tools, I believe I have a previous version of it installed already. If I open up a terminal window on my MacBook, I should get GCC, which, no input file, that's perfect. That's what I want. So it's just like if I were to telnet into a Linux server. This is BSD Unix is what this is. So I can actually run Linux commands in here. It's a Linux, Unix Linux. It's technically BCD, which is the Berkeley system Unix, but it's made on a notebook computer, so it's technically Linux, but Unix Linux. It's Unix compatible, let's just say that. And GCC, I think G++, I don't think G++, no, G++ works too. Or CC, was it CC? Yeah, CC works as well. All of the command line all of the C or C++ command line arguments work. So I could write the program right now. In fact, I have some examples. Not today, I'll show it to you after next week. Next Monday is a holiday. It's Memorial Day. There's no class. But the following week, I'll show you the source code examples for that. But what I want to do is give you something that you could possibly work on for the next couple weeks. And have you, give you something just in case you're bored over the weekend. Memorial Day weekend, you might be bored. Who knows? I'll give you something to work on. So I'll go over the assignment at the end of the class. But if you're not, if you have a MacBook and you want to install this while the class is going on, I just showed it to you, so you can go ahead and upload. In fact, while I'm here, I'm gonna install mine here actually. So you get mine installed while I'm lecturing to you, so I can multitask. All right, let's talk about Unix, and then we'll talk about threads, which is the lecture number 3. So we're still on lecture 2, and this is slide number 30 of lecture 2, where my TA told me I left off last time, which is good. Okay, so Linux, Unix. Well, okay, so I already said that Unix is on big ol' Sun hardware, HP hardware. Actually, HP UX is probably popular. Sun, everyone knows Sun. The entire internet is Unix. Actually, it's all Unix. So we do a UUCP, which is a Unix to Unix transfer to go to a MacBook. So believe it or not, actually, if you have not a MacBook, excuse me, a Windows operating system, if you have a Mac operating system, or if you have an iPad operating system, or something that's Mac-ish compatible, you'll get faster internet speed because you're going Unix to Unix. You're not doing a Unix to Windows translation back and forth. And so it's actually faster innately, so which is kind of neat. So not another selling point for a MacBook, but if you're in the market for a new computer, I would highly recommend Macs over Windows. So, all right, so Unix is limited in terms of the hardware functionality. The original Unix was an operating system for Unix for Sun boxes and for Unix Solaris, and all of the big computer systems for large companies that are Unix based. And then all of a sudden people say, well, what about Unix on a notebook computer? So the x86 version of the Unix is what everyone calls Linux, as I mentioned before, because it's made for different hardware. So we took, well, I didn't take it, somebody originally about 40 years ago or so, took a Sun system, took a Unix box, or BSD Unix or something originally, translated it over into a kernel, compiled a kernel that would work on an x86, and then we have Linux from that. So we're looking at systems programs. So Unix originally, there's a Sun, well actually on Unix, Sun Unix, there's a Sun OS, there's a Sun Windows, actually looks like regular Windows. It's a graphical user interface for it. But traditionally what we're looking at is a command line interface. And we're looking at systems programs that run on them. So let me describe Unix to you, and I can do this in without even covering anything on this slide here, but just do it in a big old nutshell, big picture here. I'm a huge company, and I have 200 employees, as an example. A huge company. And why would I want to buy 200 computers, to have them all have a computer, which is what we're doing now because it's cheaper. But long story short, I want to take advantage of economies of scale. I buy 3, 4 Sun boxes. And I stick them strategically throughout the building, and I network them together. And I say strategically throughout the building because I want to kind of spread them out into low usage areas. Because one person is probably going to connect to this thing. So I'll probably stick it on the admin's desk maybe. Or maybe on the program. Usually what ended up happening originally was all of the programmers, all of the system administrators got the boxes. Everybody else connected to it from a different terminal window. Because what we have with Unix is really the multi-user environment. So you figure load balancing, you go, what are people going to be doing with these computers? I got 200, let's say about 50 users maybe per box. Maybe let's do that, just kind of, maybe we have some good bandwidth going on between our internet connectivity. So we have one brain of the operation that's connected to another brain to another brain. We have 4 brains total. And the 4 brains are sitting on, maybe the programmer's desks or maybe the receptionist's desk or something. And they might have a window that they're connected to it, a terminal. So this is where the terminal concept came from. And these were called thin clients because they were just a keyboard and a monitor. And you connect to one of these 3 Unix boxes. And when you turned on your monitor and your keyboard, your Ethernet card is housed in a little box there, probably with like maybe a local drive or something, who knows. Probably not, maybe just a USB port or something, CD-ROM port. The network card automatically connected to this Unix box, and you were essentially your remote connection because you weren't sitting at the box. You were sitting a couple of steps away from the box, but you were connected to the box, so you got a login. So it's kind of like this login here that we're looking at. So I can have this window opened up right here, and this is one window, and I can be working away. And then I have another user who logs in, and I have another window with a totally different session going on. So this is where the original session concept came from. So if you think about the internet, and then I can do something totally different here. I can, figure out where I am and stuff like that. I can kind of, have two well, imagine 50 of these opened up on my one computer, and I've got 50 remote users logged into it, not from this screen, but from a terminal interface, from a remote networked connection that went on. So they're all sharing the same brains, they're all sharing the same processor, the same hardware, but we're looking at multitasking, which is how the entire system was designed right from the start. In fact, you can see it here. I typed in PWD for a reason. What I've got here is a users directory. Inside the users directory, I'm going to have all of my users. And so we can design the directory system so that only I have access to this bhacker directory from home, and I have a mapping to all of the other directories that I might have access to. If I list them out, I see I've got a ton of other directories available to me. When you log in with your user account, when you log in, you're going to have a different directory. In fact, I believe I actually have the ability to have, I do have the ability to have multiple logins because this is a Unix system. So I could log in as an admin, I could log in as a user, and my file system is going to be mapped to my directory. Because first thing people figure out is, well, why do you want to have everybody connect all to one computer? Well, the thing is, you can't. Like a Windows machine, you can't do it that way. But if you have a Unix box and you have directory mapping, my login script is going to map my file structure to me. All I'm going to see is what I have access to. If I move back a few levels, go up to an admin, login or something of that nature, and then I go out and I look at everything, I'm going to have access to different directories and different systems. So you have a segregated view system. It's all on the same computer, all on the same server. It can be all backed up together. So when you do, you have 4 servers or 3 servers, you back it all up. You have everybody's data. It's not spread out over 200 little desktop computers. It's all on the same server, so you can back it up, restore it, archive it, watch it, monitor what people are doing on their jobs. Because I can take a look if I have an admin perspective. I can take a look and see what is this bhacker doing on this computer. Log all of her activity, log all the other users. I have protection built into the system because I only have access to my files, my directories. Whatever I do is kept separately than everybody else, but it's all stored together. So there's like a master layout, master plan of all of this. Much better environment for originally when we started out corporate world. Much better environment to separate out all of the computer usage. Problem with that is these systems are expensive. We're looking at I don't know what the current price is for a Sun server, but the last time I bought one it was about $17,000. This was about 5 years ago, so I'm sure they've probably gone down in price, but and that was a lot of memory, a lot of good specs on it, but about 10 to 15,000 is what I'm thinking. Be lucky probably to find one under $10,000. How many of those are going to buy for the company? Maybe 3, maybe 4. Well, why are you going to do that? Well, because you have foreground, you have background jobs, you have the entire corporate system is running off of these servers. So you've got all of the financials for accounting, all the apps for applications for accounting, customer service, human resources. You load it up all on these servers, and then you essentially have all of the computing resources all held together, and then you have everybody logging into it, and then you can actually set up remote logins. So you have maybe an RSA key or something for security, and you log in from home, and there's my window, there's my programs, and you're all connecting essentially through what they refer to as a client-server environment. So the original Unix configuration met 2 categories of networking, and now I'm flipping back into a networking concept. Client server that I just mentioned, and then it was also distributed. Still running that way. So if we have company Acme Inc. that I'm describing here with 200 employees and let's give them 3 servers. We put a name on each one of the servers. We connect them all together. When you log in, you're logging into one of those servers. If you're at the company or if you're logging in remotely through one of those RSA keys or whatever, you're connecting. So we have a bunch of clients. We have 200 clients in this scenario. Hopefully connecting 50, 50, 50 maybe, or 75, 75, 75 users that are assigned. And one server goes down, well, you just connect to another one. Because what we have is this concept of distributed computing. So you can log in and you might have one application that's actually installed and running off of all 3 servers. And it's not necessarily just on one server. Pieces and parts of it might be on another server, might be on another server. So now we have unlimited amount of hard disk space, unlimited amount of processor speed. We need more processing power. If we just buy another server, spend another 10 grand, now we have 4 instead of 3. And we have the combined effort of all of it working together because we've distributed out our applications. So it's not all running on one computer. It gives us the ability to have fault tolerance and to have RAID systems and to have backup systems and all sorts of different networking concepts you'll get if you take a networking course. But long story short, that's the distributed concept is all of the apps distributed out over the big UNIX boxes. The client server are all of the separate connections all connecting to a central location, the server. So Linux gave us both. Take those 3 computers at company X, right? Add them to 3 more computers at company Y and 3 more at company Z. Put them all together, what do you get? The internet. That was the start of the internet. Started with the government, actually. Took 3 servers over here. The internet is all a bunch of connected either Sun or HPUX Unix servers. So you buy an account. You're still a client. You get what's called an ISP account, Internet Service Provider, they call it. Well, what is it? It's a login. They give you a name and a password, and they give you an IP address. They say, hey, log into that server. You logged in, and you have, through TCP/IP, you have connectivity. What do you get? Access to the public directories on all the other servers that are out there. So instead of just 3 in your company, now you got, I don't know how many servers there are, millions, billions of servers out there that you can connect to. How do you get through that? Well, you're using an HTTP protocol through a web browser. Is that really all you're doing? Yeah. Has that been around since like the beginning of computing? Yeah. That's like the first thing they did. Not as graphical as it used to be. I mean, we're graphical now. We never used to be as graphical. But nothing has really changed with the internet. However, protocols and technology and advancements in the way that we're running things has greatly improved. Now, instant messaging, port-to-port communication going on, all sorts of different advancements, but the foundational system is still the same right from the beginning. It's just a bunch of companies with a bunch of computers connected together. So we have the intranet and then we have the internet. Intranet are those 3 or 4 Sun systems inside a company X or Acme Inc. or whatever we're going to call this company. That's the intra, is those 3 computers connected together with inside of that company. And we have the internet. We take the public access to these guys and we connect it with the public access to those guys over there, to those guys. Then we have the inter, so inter is between, intra is within, which is where that terminology comes from. You still have clients. Everybody's a client if you're logging into it. So you're going to log into one server and then you're going to get access to multiple servers after that. Most of you guys probably log into the server that you have your account with. If it's, if you're on a smartphone, you have the same concept. You're going to log into AT&T, Verizon, something. You're going through an entry point through a server, and then that server is going to connect it to another server, to another server, to another server. Not all internet access is created equal. Sometimes some areas of the world have faster speeds. We're only as strong as our weakest link and the router equipment. So as technology has grown and bandwidth has grown, so has the equipment and the upgrading of the equipment. Who owns the internet? Nobody owns the internet. Well, everybody owns the internet, I guess, is the better way of putting it, because everybody's got a computer that's connected to it, right? So Traditionally, however, when we look at Unix, we're looking at systems programs. We're looking at the programs that run on that, which is kind of interesting. So going back to Acme Inc., we'll call it Acme Inc. with the 3 Sun servers in there. The programmers are programming on the systems. The users are running their web browsers on the systems. Everybody's connected to these 3 systems. And then we have these things called jobs. Jobs are the backups, the systems programs, the maintenance, all of the different, compilation in some cases for programming efforts and stuff. The maintenance of the public HTML directory, which is the public interface, because you know that the public interface is just one directory, public HTML. If you've done web browsing, web development work, you know this already. It's just a directory. You shove everything in a public directory. How do we make it public? We just change the access rights to the folder. So just the same way as we map different users with different routing to different folders. And that's an abstraction, actually, and I'll talk about file systems. It's a file system abstraction, actually, that the user gets. But long story short, we mix them all together, and then everyone runs all of their computing efforts off of those 3 computers. Well, okay, let's say if we take modern day pricing, however, and we go 3 computers, $10, $20, $30,000 if you get them on sale, they're really good pricing. Let's say optimistically we're looking at $30,000. Well, what if you have 200 users and we give them $1,000 computer each? We're still looking at saving a lot of money. Not $1,000. It's not going to cost $1,000. It's going to cost $200 or $300, $400, $500. So you take 500 times it by 5. We're still looking at, but then we got issues that come up with that. So what ended up happening is not all 200 people started the company all at one time either. So you're going to spend $30,000 for a company of 5 people because you're expecting to have 200 people. Or you're just going to go out to Fry's and buy $500 computers, or not Fry's, you're going to get some sort of a service contract, company, corporate discount, and go $200, $400, $600, or $300, $900. It's cheaper. So people went the desktop route because it was cheaper. But with the desktop route, everybody has their own files. Everything's all separated away. There's no storing of anything. Which is how then people came back and said, well, what about a database? So it's interesting how we fixed the technology with more technology. So instead of now, because now everyone has their own installed programs, has their own files, have everything locally stored because we can't afford to put Unix servers in here. We're going to buy everybody a desktop, they can just connect to the internet, right? So we go ahead about 50 years now to modern day times. Now all the companies, they want to put a database in there and have everything updated into the database. Because we're going back to the server, because remember in the day number 1 of this course I said we've gone full circle. We started out with thin clients, we got really fat, now we're back down to thin again. And which is kind of interesting because now even like Windows RT and even the iPads and all those little tablet devices are thin. Well, they're physically thin, but they're also thin, meaning that most of your stuff is cloud-based now. All your apps are stored in the cloud, or your data is being cloud stored, which means it's taking it off of the client, putting it back on the server where it belongs, actually. So it's nice. The computing world's gone full circle, and we've gone back down to thin clients. The interesting thing now, however, is that we can go thin without having to spend $30,000 because we have cloud service. So the cloud service is it's nothing more than a bunch of Unix servers all put together with middleware, is what I call it. Cloud is middleware software. It puts it all together. It gives you the abstraction of this huge data storage area, or this huge application server, or this huge web server, or whatever it happens to be used for. It's just a bunch of Unix boxes networked together. Who's got the Unix boxes? Well, the companies on them. Amazon owns them, or Sun owns them, or Microsoft actually has a pretty big cloud system, or Apple's got a pretty big cloud system. We already have the Unix boxes, so we just put another program on there, call it a cloud. It's really middleware that puts it all together and sells you accounts. So you buy cloud account now. What does that do? Well, it gives you back to the Unix concept. We've gone full circle. Now you don't have to have a big client. You have a thin little client. You put everything out there and you can connect to it from any thin client and get all your same email and everything like that. So, which is Gmail actually. Gmail is a cloud service. You're using the cloud whether or not you know it or not. If you have a Gmail account, you're using cloud service actually. All your Gmail stored offline. You don't have anything stored on your computer, by the way. So when it comes to Gmail, so you could save things locally, but most of it's coming from a central server. All right, systems programs, and then we have this kernel concept. The kernel is what really defines the system. And I talked about kernels last time, so I won't talk too much about them right now. But it could consist of everything below the system call interface and above the hardware by definition. Provides the file system, the CPU scheduling, the memory management, all of the operating system functions, and a large number of functions for one level actually. We have different types of kernels. We have, here's a Linux system structure as I've looked at last time, actually in the last lecture we looked at a week ago. We have some kernels that are fat and we have some kernels that are thin, but they don't call them fat and thin like they do clients. Instead they're micro, or they're huge, micro kernels, or micro, because they want to know, well, basically what we're looking at is we're looking at a single monolithic kernel, are we looking at multiple kernels, are we looking at a thin one, a fat one? It's all in the configuration. What is the kernel going to do? All kernels are created equal, actually. The kernel only does one thing. It provides the interface to the hardware. It sits on top of the hardware, gives us our abstraction of the operating system, so we can load stuff on top of it. We can take and create what they call a multi-purpose kernel, which is what we have now with Windows. We have a multi-purpose on the MacBook too. What does that mean? We make it small. We make it micro. We only put in there what's needed for the hardware. All right, if we're Apple and we're building a kernel for a MacBook, for a Mac product, we're pretty limited because it only works on Mac hardware. So we're pretty exclusive in terms of what we're going to support. So we have a certain Radeon or whatever, I don't know what kind of graphics they're doing now, but we have graphic support, hard SD drive support, all sorts of different hardware. It's fixed. We can make a pretty small kernel, which is why the kernel doesn't take that long to load. It's pretty stripped out. What's the kernel going to do? Well, it's going to load modules. They're called kernel loadable modules, and it's going to load them on top. So the kernel's going to start up, then it's going to say, oh, what do I have? Oh, I'm a MacBook Pro. I have this. Load this. I'm a this. Load that. So once it knows what it is and when it needs to load, then it starts loading on these things. And they're called loadable modules that the kernel loads. That supplements this itsy bitsy little kernel, makes it bigger, loads it into the kernel. What do I mean by loading it? It loads on top of the kernel, really. It's supplementary to the kernel load. Provides the driver support and the interfaces to the other hardware that may not necessarily be generic on all systems. What do we do for Windows? Well, we just have a really much bigger kernel, and we make it work for all hardware. Because how do you know if you're going to be on a Dell or on an HP or on a Compact or a Lenovo or whatever? You don't know what system you're going to be on. So you make the kernel a little bit bigger to support all hardware, and you make it more generic. And then you also make it so it's loadable. So then you have this thing called the Windows registry that loads up as a supplementary kind of traffic guard to say, well, what do we need? Well, we have this driver, we have that driver, we have this location, we have that location, we have all this other stuff. And we configure the system so the kernel doesn't have to be as intelligent. We separate the work out a little bit, take it off the kernel, put it on other system functionality like registries and indexes and stuff, so that we can find all the stuff we need and load all the other stuff that we need that may not necessarily be part of the standard system. So there's a lot more configuration work that happens on a Windows system by nature, which is kind of interesting because hardware manufacturers have kind of done the Mac route in a lot of ways. When you load up a Lenovo computer, you get a Lenovo built kernel. What are you going to do? Well, they're going to streamline it. Strip out everything, get an agreement, an OEM agreement with Microsoft that says, hey, we're gonna put this on our hardware. We don't have all that other stuff. We don't have to support all that legacy stuff, but we have touch controls, and we have this, and then we have that. So they're going to custom build it. They call it OEM, original equipment manufacturer. Going to come in, and you're going to get a Lenovo's version of Windows. You know, in the old days, they used to give you the disks. Now they just load it on an extra partition on your drive. And you can go back to it. You try to load another one on there, it might work, but it's going to be heavier, thicker, fatter, because it's not as streamlined. So long story short, if you're ever updating your operating system, make sure you do it through the manufacturer who has provided you the original operating system. Get those drivers, get that upgrade, because if you just go and you buy an upgrade to something and you install it, it's going to be heavier. It's not going to be streamlined for your hardware. So anyway, so we got the, here you've been staring at the big picture here. We got the users up here. We have the shells in the command line interface, compilers, interpreters, system libraries sit on top of that. And then we have, this is the Texas cheese toast I was talking about. We got 2 pieces of cheese underneath the patty here. This is the patty in the middle, or the veggie burger, whatever you want to call it. Or the whatever happens to be in the toast. This is the bread on the top, the bread on the bottom. What do we have here? The system call interface is one of the cheese levels, and then the kernel interface to the hardware is another cheese level. Normally I always think of this up here, and I think of the kernel and don't talk about the hardware, because this isn't really a hardware course. But what we have in terms of the middle, and this is the job of the kernel, which is what the slide's pointing out. It's going to do all of the low-level stuff. So in this course, we're looking at the kernel. So probably from, let's see, we're going to start in with processes today. The next topic is going to hit directly into CPU scheduling. So we're talking about kernel functionality, CPU scheduling, memory management, file system, disk system, terminal hardware, networking systems, with a little bit on the hardware, but not much. It's going to be primarily a software-oriented kernel course. Underneath here, this is where you take computer architecture and you learn about the hardware. That's go on. Oops, just dropped my mouse. There we go. All right. Microkernel system structure. So I talked ahead a little bit, so let me catch up, see if I missed anything. Moves as much from the kernel into the user space. Micro makes it small. It's a very small kernel. Communication takes place between the user modules using the message passing that goes back and forth. Benefits, it's easier to extend the kernel. Once you compile the kernel, you have to recompile the kernel if you want to change something. So what if this new developer comes out and makes a USB 5.0, you know, or it's 5.0, the kernel's not going to know about it. You got to recompile the kernel to add in driver support for that, or if it exists, and how are you going to know what everyone's going to make? So I think we're only on 2, so maybe I should have said, well, 3, so I should say 4 maybe. So easier to port the operating system to new architectures. Yes, it is, especially when you've got different hardware from different manufacturers and you can load it on after the kernel instead of relying upon the kernel to support it. More reliable, less code is running in the kernel mode. Only the safe stuff, isn't it? It's more secure. Determinants, performance overhead of the user space. Yeah. If you put everything in the kernel, and here's how the kernel loads. Kernel loads first, it's going to be in the lower memory banks. Anything lower in memory is faster running because you don't have to go search through the entire set of memory to find it. You just go, and especially if you can fix it at a certain point, you just know the memory address if you're the kernel. Read, write. No searching, because memory management, searching through the memory is time consuming. So long story short, we fix it where it's located, we can read, write to it faster. When we load it after, it's anywhere, which means slower. It's going to run slower. We can't just automatically go to it. We don't even know where it is. We got to go find it. So it makes the system run slower. So microcomputers, microcomputers, but microkernels are efficient when it's the kernel. But if you take everything out of it, make it all user level, then what you got is you got a pretty slow running computer. You gotta, so there's been tricks throughout the years to make things run faster, load things, different sequences, and if you think about that's what the registry did. The registry basically set the memory location for all your drivers, created a lookup table. So after everything got loaded, then it goes and looks at the registry, which means you messed the registry up, you messed everything up. Because the registry is the traffic guard telling you where everything is. You go over to the table, and if it's not in there, it's not loaded. Even if it is loaded, it's not going to read right. So I don't know why people insisted upon cleaning up and changing and modifying the registry. Never change your registry. It doesn't really matter how big it is either. It doesn't really matter. It could be huge. It could have a bunch of extra stuff in there you don't even need. Not a problem. It's just sitting there. It's just a lookup table. When we go to find something, we got to be able to find it. It's not going to search through stuff that's not related to it. So, which is kind of interesting, because the philosophy of most Windows users, when you, well, some levels of beginner users is, you know, they look at the Norton tools and stuff and all of the different, you know, clean my hard drive. And cleaning a hard drive makes sense. Cleaning a reg does not make any sense, actually. It's not going to affect the efficiency of your running. In fact, if anything, it's going to screw it up in the long run. So here's the Mac OS X structure, where we have a BSD kernel on a mock system, actually a BSD Linux environment running off of a mock kernel, by the way. So this is the kernel environment here. We have an abstraction that's running above it. It's a Unix version. And then we have the application or the common services that run on top of it. So, and we have modules that we're in. And the reason why I'm showing you a Mac system is because it's more representative of Unix, and we're talking about Unix today. Windows is going to have a different structure to it. It's not going to look like this. Because Microsoft Windows is not Unix based. So it's going to look totally different. Is it more efficient? Some might argue and say, yeah. So it's on a, well, some people, I still get YouTube users actually that argue with me about DOS. DOS, I keep saying this over and over again, and people keep arguing with me. DOS, Microsoft DOS, MS-DOS is still part of Windows. It has not gone away. But I usually, if I go on my YouTube site occasionally, like every once a month or so, or twice a month, oh no, you don't know what you're talking about. DOS is gone. There's no more DOS anymore. Like, come on, people. DOS exists still. You can go to a command prompt. You can. It's a shell. Yes, it is a shell. It's not the underlying. But in the old days, we had DOS, and we loaded Windows on top of DOS. Now it's all integrated together. But DOS is still there. So it's not the, it's not the underlying operating system. Before, well, DOS stands for Disk Operating System. It was the first Windows. Actually, it wasn't even new. There was PC-DOS before there was MS-DOS. But it was the first operating system for users. Well, who likes command prompt? Nobody does. So then we had Windows. Well, what's Windows? Well, it's just a graphical user interface to the DOS. And that's how it was. You booted up your computer, you got to a DOS prompt, and you typed in WIN, pressed return, and it loaded up this program called Windows. So we still have that same thing going on, but Windows loads up automatically now. If we want, we can shell to a DOS prompt. It's backwards now, but it's still the same. It's still there. We're not loaded like this. This is different. This is a microkernel loaded on top of hardware where you have an operating system shell loaded on top of that, which is different. It's not MS. There's no MS-DOS on a Mac system. So we have the kernel loadable modules, as I mentioned before, or sometimes just referred to as modules. Most common operating systems implement kernel modules. You can build kernel modules. Most of them are written in C. If it's Unix, Unix was written in C. The kernel is compiled in C. It's all C code. So you compile it using a kernel compiler kind of utility. You can configure it, compile it. Actually, building kernels is fairly easy. If you take a Unix course, you build kernels in it. Or you should at least look at the kernel build process. Not bad. It takes a few things to get used to. You got to download all the source code for the kernel, but most of it's menu driven these days. Kernel config programs, you just go through, make some settings. Do you have this? Do you have that? Answer some questions about the hardware that you have, and press a button, compile it. Take the little kernel file. What is a kernel file? Well, it's just a C program. It has a slightly different extension. It's not run by the runtime environment on the system. Instead, it's loaded by the boot sequence. So you take that little thing and you copy it onto an SD card, or you copy it onto the computer itself through a serial port. They usually call it, burning it onto a ROM chip. Then you can have an embedded Linux system where there is no user interface to it. The hardware boots up, loads this kernel. Kernel provides the system interface. Well, that's how your microwaves are working. Microwave ovens, your TV sets, your watches, your smartphones, they're all working on microkernels that are booting up from hardware. Some of them are written in Android, some of them are written in well, partly Android/Java, kind of, well, Java. Some of them are written in C. You know, they have if you're curious about this, look up UC Linux. It's embedded Linux. We have embedded Android now too, but embedded Linux is where it started out. You're going to get more jobs in embedded Android because everybody's Android now. All of the tablets are embedded Android. So it's just why do you need that? Well, you decided you're going to make a tablet computer. You're going to need an operating system for it. So you went out, you made this little CAD drawing of the board. You've got some, some fabrication house is putting together some boards for you. You got a processor chip and memory chips, and you got your I/O lines and everything because you studied electrical engineering perhaps, and you made your own hardware. First thing going to be a problem is how you're going to get some software to work on it. So then you get some open source Android and embedded Android kernel code, and then you compile a kernel and you stick that on the board. What's that going to do? It's going to be a low-level interface. It's going to tell you what memory location is this at, what kind of buffer memory is it going to use, how we're going to operate the hardware. So you speak to the hardware through the kernel, you load the kernel on there, and then you can load anything you want on top of it. And lo and behold, load Android on top of it. And voila, we have a $99 or $49 Android device, extremely cheap at your local computer store, loading Android. It just has its own little kernel on there, and you load it up. Sometimes it says what it is, So some kids screaming in the hallways. All right, so we have modules going back to here. So it's uses object-oriented approach because we're taking code from all different sources and we're putting it together. Each core component is separate. It's a separate piece. Talks to each other through known interfaces. They call it kernel loadable modules because it's loaded by the kernel. The kernel knows how to load it. It's just got a program that loads it. So each is loaded as needed. So you have delayed loading in most cases. So if you go talk about the kernel, you're talking about loading. If you're above the kernel, you're talking about linking. So we have DLLs, which is actually kind of interesting. So most of the Windows operating system is loaded with delayed link libraries instead of kernel loadable modules because you're going to delay the linking and the loading until after the kernel is already loaded because that's how you're going to do it if you're Windows. So you have everything. In fact, this happened around the XP days where everything turned into a DLL, which makes it great because it's extendable, upgradable. You just change the DLL file, reboot the system, and then everything's loaded. DLL stands for Dynamically Linked Library. Kernel loads up, has everything ready, and then there's a whole to-do list that the kernel's got to go through. It checks the registry and says, okay, what do we got to load? You got to load this DLL, that DLL. Here's 10 DLLs, load it up. So it loads them up into memory, and then sends the address where it's located after it finds an available piece of memory back to the registry, updates the registry, which is why you can't change the registry while it's running because it's loading. It's got memory addresses in there that are going to change when you can't change that stuff. So then a program loads up. What does this mean? A DLL is great because you got it loaded once, one module. Think of it as a module, and it's controlling your CD-ROM drive as an example. It's loaded up, it's at one memory location. All the programs that are going to use it are going to link to that one driver that's already loaded. You're not going to load up the driver 15 million times to load it all over again for every time you're going to use the CD-ROM drive. However, there's a lookup. Because it is loaded, you have that time to go to the registry to find where is it, and then go over there to go look for it. But it's still faster than loading it up fresh or loading it multiple times. So it conserves memory, makes it load faster, makes it more efficient. Same concept as the kernel loadable modules, same thing's happening except for the kernel's keeping track. So in the kernel system on a non-Windows system, on our Unix or Linux background, system, what you're looking at is a table in the kernel space because we have a separated user kernel mode and the kernel's keeping track of all those loaded modules. A little bit harder to configure it, a little bit not quite as extendable. because you're going to take up kernel space, you're going to make the kernel run slower because kernel's keeping track of all that overhead. So that was pretty wise to move it to the user level, link it with a registry, because then you got a faster running kernel. What you want, a faster running system. So there's a little variation in terms of the scheme, but if you're building an operating system from scratch, these are sort of the things you're thinking about. Where am I going to stick the modules? If I don't stick them in the kernel, I have to stick them somewhere, and who's going to manage the modules? Is the user mode going to manage it, or is the kernel mode going to manage it? Because it could make for some performance problems or performance differences. Here's a Solaris module approach where we got a core Solaris kernel, and we have scheduling classes, devices, bus drivers, miscellaneous kernels, all these little things that the kernel is keeping track of. So if you're going to have the kernel keep track of it, you can make it protective, which is where you come up with this terminology that's called a protected operating system. It's protected. It means you can't touch it because the kernel's going to... Most of your smart devices are running that way. The user mode cannot touch it. You can't even get to it, which means you can't take the system down. You can't crash it. Can you crash a Windows box? Sure, why not? Not protected. They moved it all out. So yeah, it runs faster. It will run faster because you took it out of the kernel space. You made it more flexible. All those modules that you're loading, you just reduce the number of modules you're loading if you want to make your system run faster. Just take out the crap. Take out the bloat that's in there. If you do that, then you got a pretty fast running system. However, you could disable, it's not protected, you could disable it completely by removing a module. How many times does that happen to people? A lot, actually. And then, oh, it doesn't boot. Oh, it doesn't work. Or it just crashes on its own because it upgraded itself, and how many upgrades have gone bad in the past? Many of them have. So we're looking at a non-protective, and that's what the protected means. It has nothing to do with security. Is it kernel protected, or is it not kernel protected? Kernel protection means the kernel's in control of it. It's below the user level. It's going to keep track of everything. It's going to manage itself. If it manages itself, it can determine its stability, and it can protect itself from unsafe loading and unloading. Do you have as much control over it? No. You can't really do very much to your smartphones. You can't do very much to your tablets either, actually. Some tablets you can't even load a new operating system on it. That's how protected it is. However, the tablet's never going to die. It's going to run constantly. It's never going to crash. Never going to have any memory leaks. Nothing's going to happen to it. It's going to actually run safer. So. We also have this concept of virtual machines to deal with. So a virtual machine takes the layered approach. So if you think about it, isn't your desktop sort of a virtual machine? Going back to the Windows concept, you loaded up DOS. You loaded up an operating system on top of DOS called Windows. And I call it an operating system, but it's really a desktop. You load up Windows, you load up something on top of Windows, you load up something on top of that, and on top of that again. Hey, thanks for shutting the door. It's like there's some kids screaming in the hallway. Hopefully none of your kids screaming out there. Otherwise you'd be out there trying to shut them up, hopefully. Anyway, long story short, I know I sound so, like, unsympathetic. Long story short, it's layered on top of layered on top of layer on top of layer. Well, isn't a virtual machine just another layer on top of that? So, but the thing with the virtual machine is, and they're really getting a lot better with the concept, move it down a level. So instead of loading it on top of the desktop, load it where the desktop's being loaded. Load it on top of the kernel. So it's still loading on top of the kernel, but it's not loading on top of Windows, or it's not loading on top of a Mac OS X interface. It's or Lion or whatever it is, but it's loading right there on top of the kernel at the kernel level. So it's still using the same kernel. It's just loading a different desktop for you, which is a lot. So we're actually going more and more the virtual machine route, because once you have a kernel, what does it really matter what you're loading on top of that? So that's how on this computer here I load a virtual machine software actually called Parallels. There's also VMware. There's this other one that I have. I can't remember the name of it, so I'm going to look right now. VirtualBox, made by Oracle. So I've got Parallels. These are virtual machine software programs that allow you to install operating systems on top of the current operating system. Well, they run almost at the same speed as the regular operating system these days. So don't be afraid to venture out into it. In the old days, they used to run on top. Now they're running at kernel level, right above the kernel, right on top of the system call interface. And they're doing the same thing. They're just, the software is emulating the right kernel. So it's a kernel filter to turn the host operating system kernel into the one it needs for the operating system that you're going to install on top of it. So anyway, it's just another layered approach. Logical conclusion treats the hardware in the operating system, a kernel, as though it were all hardware underneath it. Provides the identical interface for the underlying bare-bone hardware that's needed for whatever it is you're loading, and gives you the illusion of multiple running processes, each with its own processor or virtual memory as well. So resources of the physical computer can be shared and created over virtual machines. So we have the CPU that can create the appearance that users have their own processor, and that the kernel actually has its own, the kernel of the host virtual machine actually, the host is providing the virtual machine, but gives you the illusion that that virtual machine has its own processor, but it really doesn't. It's sharing the underlying one. People are doing this for testing, and here's kind of like what it looks like, and it kind of gets into this process concept. You build process groups. You put the processes on the system, and I'm going to talk about processes coming up shortly here. And then you load kernels that are running in their own processes. And here's virtual machine 1, 2, 3, and this is the software. This is the virtual machine software. This is the Parallels or the Virtual Box or the VMware down here. And this is machine 1, 2, and 3 with each 3 different running kernels with processes running on top of it. All of this really is a memory abstraction. That's how it can actually run at a pretty decent speed. You're not running through anything. You're running on the hardware through the software. And you're creating your own separate abstraction. So in essence, you're just juggling memory around. So if you're going to run this, you're going to have a lot of memory. I hope you're going to, you're going to have excess memory, and this is the only time you're really going to use that excess memory, is when you're juggling different virtual machines on there. So, all right, here's a VMware as an architecture. I'm not going to go through the different concepts. Some people are actually familiar with virtual machines from a certain point. If you're not, you can download the slide sets, lecture 2, read through it a little bit slower. But here's an example of the original version of VMware. It's changed throughout the years, but it sort of looks like this, where we have the CPU, the memory, the hardware devices, then we have the host operating system, and then this is the VMware part, everything above it. We can run applications on top of the host operating system, or through the virtualization layer, the VM, where we're running the different, here's a FreeBSD, a Windows NT, a Windows XP. So this is an old example, but we have the guest operating system running on top of it with the virtual CPU, virtual memory devices that are running underneath. Which brings us to this concept. Most people have heard of Java, right? Java is running as a virtual machine. So that's how we get the virtual. That's why we're talking about virtual machine. Most software development is running this way. Well, if you're using Java or anything Java supported, what does that mean? Well, Android is virtual machine. It's running on JVMs. What's a JVM? Well, we have our Android devices, right? We got our Samsung, our Motorola, all different hardware, all with different Android embedded kernels. One kernel built for each one of the specific hardwares to analyze and to load all the modules and do everything we need to do for each one of the individual hardwares. Then we load a huge old Android JVM on top of that. And then voila, we have Android. Depending upon what version we load, we get different versions of Android, but it's all Java based. So that's why people like Android, because it's very simple. It loads on anything. In fact, you can make your own phone if you wanted to. You got to compile your own embedded system kernel, and you got to load it. It's a lot of work to make your own phone. It's probably cheaper just to buy one, actually, but it's open, which means it's all the source code's available to you. It's open source. So the money you're spending on the phone is on the hardware. It's not on the operating system. That stuff's free to the person who's making it. So Java works with a JVM, Java Virtual Machine, which is a machine, virtual hardware. So what do we get? most people who install the JRE on their computer, runs on Windows, runs on the Mac, that's a Java runtime environment. That's the runtime. Same as the Windows runtime, same as the Mac runtime, but it's for Java, runs on JVM. So you run the JRE, gives you JVM support, then you have the JDK, gives you the software interface for programming, gives you how to compile the programs for the JVM. So what do we have here is we have the host operating system, and then we have the Java interpreter that works with the host operating system, and then we have what's called the class loader. What is that? The module loader. Loads the classes. So, you know, every Java program, if you've done any Java programming, you don't have to do any Java programming for this class. But if you have, some of you have taken my Java class actually, you create a bunch of .class files. The .class files get loaded up into memory. Well, it's the JVM and the virtual environment that's loading that, it's managing that. And technically, it's using economies of scale, so we only have one class file loaded for each type of class module. It just stays in memory. And then we have a linker system, very similar to a registry, that we can link everything together. And then we can turn this into a distributed multi-user environment by looking at the EE version of Java, which is the Enterprise Edition, which gives us the most popular feature, I think. Well, there's two of them. The servlets are popular, but RMI is pretty popular. So RMI is remote method invocation, which means instead of loading it on one computer, we'll load it on 10 computers. And we'll store the modules everywhere. And then we'll use this thing called an RMI registry. We register all the components with it. Doesn't that sound like the Windows registry? Very similar. We create this registry, and we put everything in it, and we say, oh, where are you located? You're here. Okay, put it in a centralized registry that's going to keep track of all the loaded memory. And then now we can take and distribute all of this memory all over a bunch of different computers. And then we can link them all together through the centralized registry that the register manager is going to look at. So when we want to load something, we go to the manager and, hey, where is that thing located? Look in the registry. Oh, it's over there on computer X over there. Okay, and that one's on computer Y. Okay, good. And then we link it all together and we use the network to support distributed computing. Again, going back to UNIX, it's the same concept, but we're doing it through a virtual machine. So we have to create the abstraction of the underlying UNIX system for that distributed computing to go on. So, which is kind of interesting, actually, the way the technologies work. So, which works a lot different than C++. So, to be fair, let's compare it with .NET, not in here. The same kind of similar concept, actually. We load the framework. Instead of calling it a JVM, instead of calling it a virtual machine, we call it a framework. The old days, we loaded the framework on top of Windows. Now it's loaded inside and embedded in there. Just like DOS got embedded in there, so now that .NET's inside of Windows now. So we don't load it as an afterthought, although we can, and we can still upgrade it, which is interesting. And we can downgrade it. We can go back to previous .NET versions as well because some applications need it. Problem with .NET is that it's only supported on Windows. And if Microsoft got its way and the entire world was using Windows, that would not be a problem. But the entire world does not use Windows. So Java is supported on Windows, it's supported on Linux, it's supported on everything. So most people have realized that Java is kind of taken over only because they're cross-platform compatible. .NET's not. Are they really providing the same functionality? Yep. They're giving us distributed networked computing. One of them's limited just to Windows, the other one's limited to the entire world. So which one do you think is going to outlast it? Well, this one's free, by the way, and the other one is a paid for-profit company as well. So that is by a for-profit company too, though. Oracle owns Java. So originally Java was by Sun, if you remember, and it was not, what should I say by? Java itself was open source to begin with, but it had Sun support. So it needed a big company to kind of help it. Now it's mostly, well, it's all Oracle. And then most people can remember probably the Microsoft Java, what did they call it, Java++ or something? I don't know what they called it. They wanted to like commercialize Java. Thank God they lost that because Java is still free and open source. But then they were suing Sun for rights or something. I don't know. Don't quote me on this story, but look it up on the internet if you're interested in all the drama that happened with Java in the past. Microsoft tried to get its hands on it for one point. This was pre.NET. So then they went the .NET route. So I'm thinking they originally wanted to incorporate Java into there instead of .NET, which would have been a smarter move for them actually, but they didn't get their way. So we got .NET out of that. So operating system generations, we're looking at different generations of design to run on different classes of machines and systems that are configured for each one of the computers themselves. So if we separate out the components, then it actually survives a lot longer. As an example, the bootstrap program and the booting sequence, separating it out, and then the ROM, and then the BIOS of the actual hardware itself. If we make the BIOS as a system program that only reads the hardware and gives us the information about the hardware, then we can send that BIOS information up to the bootstrap, we can send the bootstrap up to the kernel, and then we can have the kernel take over. So if we layer it all out and put it into different job groups, then we can essentially have more flexibility. And when that started happening, what we ended up with is this bootloader program and boot sequences. And then all of a sudden people started talking about, well, what do you mean by boot? When the system boots up? Well, there's a sequence to it, and then depending upon the hardware, the sequence does vary a little bit. The operating system is, or the kernel I should say, is the last sequence, or the last part of the sequence. Small little program called what's called a bootstrap loader. Loads and locates the kernel and puts it into memory. In UNIX, Linux systems, we have what's called a bootloader, which is a little, sometimes actually even a graphical user program now that loads up and says, what would you like to load? A, B, or C, and you select one, and one of them loads Windows, the other one loads Unix or something, or one of them loads the Mac or something, Mac OS X or something. You can still put a bootloader on your computers these days as well. It's still supported. It's just a little piece of program that's loaded in a little piece of memory, usually the starting location of your hard drive. And when your BIOS boots up and sends power to the hard drive loads up, the system tries to read it, reads the first couple of blocks and goes, oh, bootloader program. Okay, load up the menu. And you select from the menu, and then from that point, the user's deciding what sequence to go through. So put some sequences together. Firmware is used to hold the initial boot code. And then most of it's stored on the hard drive actually. So we all know if you want to take somebody's system information, you want to take somebody's computer, you just rip the hard drive out of it. You don't need the rest of that junk. Just take the hard drive out of there. So call it junk because most of it is junk these days. So. And people are going to disagree with me on that one too. So I just like saying stuff people are going to disagree with. It's kind of interesting. It's actually kind of interesting only because it tells me who's actually listening to the lectures. Wow, this person actually sat through the whole lecture. Wow. They know how many times I mispronounced something, or they know I called it junk. It's actually kind of flattering, actually, when someone actually listens to it. So I don't know. If you're not familiar with what I'm saying, I put these out on YouTube. So it's ITU students that are watching these lectures, and it's people from the general public that watch the lectures. So it's interesting. The general public has some interesting comments, and I appreciate the comments actually because it helps me. So one of my biggest things, and I have been working on this actually, is staying on topic. So to get back on topic, we're transitioning into chapter number 3, processes. The other complaint I usually get is, why don't you just break these out? Okay, so the average YouTube video is what, 10 minutes? Could you imagine how much work that would be? Okay, stop. 10 minutes are up. Okay, stop. 10 minutes are up. Stop. Because you're taking a traditional college course, which is going to go for a couple hours, hour and a half, 2 hours. I'm not going to break it up. So. But I had a nice, pleasant YouTube user who said, well, you could just pause the video. I'm like, yeah, you could. Just pause the video when you're done watching it. So that's for you too. When you go back to look at these lectures, I have some students, ITU students, that go, oh, it's a 2-hour video. How do I need to know what I'm supposed to know out of this thing? Just pause it right down where you left off, go back to it later. And you can break it out into 10 minutes, 15 minutes, 20 minutes, whatever you like. Processes. All right, so let's start in with the concept of processes, and then what I'm going to do then is after I get over the basic concept, instead of giving you all the process stuff today, I'm going to stop this video and actually make a separate one to go over that assignment for you, assignment number 1, and then gives you something to look at for, because there's about a half hour left of the lecture part, so just in case you're trying to pace yourself for lunch or something. We'll be out by 12:30. So. Alright, so the process concept, process scheduling, operations on processes, cooperating process, inter-process communication. So we have multi-threaded processes, multi-threaded programs, multiple process programs, multiple users, multiple. You put the word multiple into a sentence or into an expression and you're talking about operating systems, you're talking about processes. So by definition, and if you want to know an easy way of remembering what a process is, it's a thread of execution. And then the people go, well, what's a thread? Threads and processes could be the same thing, but we have this thing called mapping. So the thread is the abstract word that's describing the sequence of steps or the CPU instructions. You take those instructions and you put them inside of this abstract word, again called thread. You put the thread inside of a process. You run the processes on the computer. That's why we have a processor. We have a CPU, Central Processing Unit. So going back to day 1 of Computers 101, there's the CPU. Well, most systems started out with one CPU, which means that one thread can run at any one moment of time. Only one CPU can process instructions. Then we have 2 CPUs. If the 2 CPUs are separated out, soldered separately, channeled out separately, and are actually running as 2 separate CPUs, then you have 2 threads that can run simultaneously. Yet 3, 4, same concept. So quads, about as big as we got right now, 4 CPUs running on that thing, and if you can afford that computer, it's about $10,000 or so. Because the CPU is the most expensive part of this entire thing, actually. You can buy a board for $100. You can buy everything for about $100, $200, and you're going to spend twice as much on the CPU if you're going to build your own system. Better yet, put multiples in there, you got twice as much compounded on that as well. So the CPU has a speed that it can process at, and that's what we call our processor speed. That's how we know how, such as 2.4 gigahertz, as a 1.7 gigahertz. When we buy our computers, we look at that number. And for the longest time, we had 2 core duos and dual cores. And we had all this different terminology being used that confused the world confused consumers in general. In fact, most consumers are still confused over it. Do we have 2 separate CPUs running as one? Because here's what happened. We overproduced CPU chips. We had more chips than we had computer boards. So you take 2 lower ones. So let's say you've got a 2 gigahertz system. You want to create a 2 gigahertz system. Well, can't you just take a 1 gigahertz and a 1 gigahertz, put it together, and make it a 2? Well, that's what they did. So it's 2 separate CPU chips that are connected together. They're working as one. So it's duo. It's together. They're a duo. They're a duet. They're singing together. They're processing together. Well, really, it's a low and a low. Isn't it better to have one fast one? So for the longest time, consumers were extremely confused because they had these HP computers that were duos. They had 2 chips on them. But they were cheaper than the single ones because it's going to run slower. It's like if you have 2 people do the same work simultaneously together, sometimes it runs a little bit slower. Just have one smart person do it. It's going to run faster than 2 not so smart people working together. And I said not so smart because they were slower. You still have one. You got 2 chips, but you still got one process running simultaneously. Then they got smart, and then they eventually, within the last couple of years, actually introduced true separate processing. So if we have multiple processors running simultaneously, and at most we got 2 right now going on in your average computer, we have some phones that run this way too. actually. Then you can separate the workouts, because everyone's still using a process concept. You can take the separate processes, route some of them over here, route some of them over there, and then you truly do have simultaneously running processes. And you have, probably at most modern day technology, what most people can afford, you got 4. You're lucky to get 2 right now. So you can do on a cell phone. Actually, the Androids, but the Bionics and most of the newer Android, more expensive Android phones, Motorola phones, have 2 processors running separately. They're not connected, which is fantastic. Most of the higher end MacBooks have them both running separately as well, which is much faster. Because what you have is different types of processors and different types of work that you can do. So going back to those cheap HP computers, I can pick on them because they all came from Compact and they were really bad design to begin with. So you get 2 low-grade processors and you stick them together, and you don't put a GPU on there. Graphics process. So we have a C for computer, for central processing unit, and we have G for graphic processing unit. Don't put a graphic processor on there. Just put these 2 lousy CPU chips on there. Link them together so they're really running as one. Forget about video RAM and forget about GPU, and you got a fairly cheap computer going on that's going to run really slowly. So, which is kind of confusing because you give all this to the user and reads the box. Oh, we have Core Duo and all this stuff on here, right? And the thing doesn't run as fast as the computer you replaced it with because it's really low end. So, okay, GPU. For graphic intense systems, if you don't put a GPU on there, you're using the CPU for it, which defeats the purpose of a Core Duo, defeats the purpose of 2 processors. So what the phones are doing now is you got one for services, one for apps. So it's dividing the workout among all of the different processors to make it run efficiently. And then you have an operating system concept of how am I going to work with these processes and how am I going to map the processes. So let's go back to threads. In fact, I'm just going to go this way a little bit here. I'm going to talk about mapping before I talk about anything else, which is kind of a different way of doing it. But mapping is what usually confuses most people. Context switching, sessions, terminal. And watch mapping is not part of here. Let's see, communication modules, direct communication, personal communication, syncing. This is like a 3 or 4 set lecture here. Marshalling. All right, mapping's not going to be in here. So let me just tell you the concept of this, and I'll tell you where this and why I'm mentioning this actually. The mapping comes into place when you have multiple processors, and we have different types of processors. So let's look at the best case scenario. We have 2 separate CPUs and we have a GPU. Then if we have threads of execution coming through, we can map multiple threads to different processes for different purposes. So if we have a process running on a GPU and we have thread over here for this functionality, thread over here, we can map them all to that one process, run that one process, have that process running on the GPU while other work's being done on other processors simultaneously. It gives us more flexibility. So when we write a systems program, we talk about threads all the time. And what I'm trying to do right now is tell you the difference between a thread and a process. If you just think about the concept of the definition, doesn't normally make any sense. Because a thread of execution, well, is it like a command? Is it a program? It's an instruction. A thread is a user mode concept. A process is a kernel concept. Kernels run processes. We have CPUs that run processes. Processes go through process scheduling. So we have a CPU scheduler. It takes processes and runs them through. Just know that at any one moment in time, you might have multiple threads mapped to one process. So you could have multiple processes mapped to multiple threads as well. So you have this thread, you can map it to this process, that process, that process. Or you can have the thread itself mapped to a single process. Most systems have experimented with all these different mapping techniques. We're now down to a one-to-one. One thread mapped to one process. So now in modern day computing, when people talk about processes, it's really a thread. There's a thread of process. So then it gets confusing because we don't have the abstraction anymore. So we have GPU-bound threads. They go to thread processes that go to a GPU. We have CPU-bound thread processing. And then we have I/O-bound threads. So we have the CPU as the main traffic guard in the entire system. Everything goes to the CPU first. That's the slowest, that's the weakest link on the entire computer. So if you want a fast computer, buy the fastest CPU chip you can possibly find. Then you get a fast computer. It doesn't matter how much memory you got on there. Nothing really matters except for that speed of that CPU. So because every instruction must go to that CPU first, and you don't want that to be the bottleneck. So it goes and then it says, the CPU will say, hey, you know what, you're really graphic bound. Your thread is marked for graphics. So then it goes to the graphics CPU, graphics CPU runs it. Or maybe it goes to math coprocessor. Or maybe it goes to an I/O queue. So when I talk about thread scheduling and process scheduling, it's the same concept. So throughout the lecture I'll say threads, process. For all intents and purposes, there originally is a difference, but conceptually right now, think of them as the same. And then you'll go, well, I have to make multiple processes. Why am I using a pthread library? Because you're using POSIX threads. Well, thread isn't a thread process. From a programming perspective, it's called threads. CPU perspective, it's called process. The mapping right now is one-to-one, so we don't have to worry about all the different mapping schemes either. So where people have tried to experiment is the multiple mappings. When we get multiple CPUs as common every day, we're going to get multiple mappings again. We're going to go full circle. And we're already getting multiple mappings right now in modern day configurations. Because why limit yourself to one thread to one process? When you can run multiple threads now, you can run multiple processes now. So you just take all those threads and map them all to that process over there, and take all these threads and map them over there, and then you can get a lot more stuff done. Because you don't want an idle CPU. If you have an idle CPU, you're not getting anything done, which is actually kind of funny. Because you take the modern day computer hardware, which is broken out, and you load an operating system like XP on it. XP never worked with multiple processors, only has one CPU scheduler with one process, doesn't know about multiple. So if it doesn't know about multiple, the processor chip on the board that you spent so much money on is getting dusty. Because it was going to get dusty anyway, but it's not working at all. But it's actually causing you resources because it's taking your battery life down too at the same time. But long story short, the operating system needs to know about the hardware. The hardware's got to be configured to work with the operating system. There's definitely a relationship between the two. So your Windows 7 knows about two processors, can schedule it faster, which is why you take the same hardware with two processors, you load 7 on it, it's going to run faster than it will with XP, because XP only knows about one processor. Anyway, so let's see, process concept. So what is this that I'm talking about? Operating system executes a variety of different programs, batch systems, time-shared systems, all sorts of different things. We call them jobs. They're jobs. If you don't want to call them a process, it's a job. Textbook uses the terms jobs and processes interchangeably, actually. So the process is a program in execution versus a thread of execution. It's a whole program in execution. Process execution must progress in a sequential fashion. We still have sequential processing going on. Think of your computer like a calculator. Actually, the first calculator was the computer. So 1 + 1 = it's still a sequence. Everything is still being processed that same way, which is kind of interesting. Process includes a program counter. We got to know where we are in the process. We got the stack, and then we got the data section. So in my programming classes, I usually start out with this here when I talk about runtime. This is what's runtime. This is runtime. So runtime is one of those words that's commonly misunderstood by programmers. What do you mean by that? And if you go and you take a comprehensive computer science master's program, they say, describe the runtime environment. It's a great question to ask because it's like most people are totally confused about it. This is runtime, by the way. This is memory abstraction. 0 to whatever happens to be the max. We have the program text. What's that? That's, you take the exe file, you look it up in a hex editor, you see a bunch of weird numbers and symbols. That's what's there. Because you're not going to go and read and write. Runtime, by the way, for those people who have never heard the term or are not familiar with it, when you double click on a file, you've entered the runtime. When you've typed in ls, you've entered runtime. Runtime is how the operating system is going to control the running execution of that program. So it's going to take the program, read it from the disk, and load it right here. Because it's not going to go back and forth to the disk. So that's too slow. And the other concept of memory, not a bad idea to memorize or just to know offhand, everything closest to the CPU is the fastest. So registers are another form of memory, much faster than main memory. Cache is faster than main memory. So when you go to spec that computer out, you want cache on your system. You want cache memory, and you want a fast CPU. It doesn't matter how much extended memory you have. Chances are you're not even going to use it up. And extended memory is what I'm talking about in terms of DRAM or SDRAM, or RAM. It's not SDRAM, DRAM, RAM that's out there that you're going to load on RAM chips. Usually have 2-4 gigs of RAM on that. Actually, MacBook computers will run with less than a gig. Older systems now we need 1 gig, 2 gigs. That's all you need. The thing will run much faster than a system with 8 gigs of RAM on it in most cases. Alright, so this is memory, program text. This is the machine code that doesn't look good. This is empty until we start running it. In the data section, we have all of the variables that are going to be stored from the stack. When I draw this upside down. I put the stack here, and I put the heap up here. It doesn't really matter. All of this is reserved for these two functionalities, the stack and the heap. The heap is memory that if you're a C++ programmer or a C programmer, when you've created pointers, your pointer memory gets allocated right here. It's called dynamic memory, and it's dynamic memory allocation. So this data down here is called static data, or static allocated memory. So when I went integer I, I'm assuming you know something about programming. You go integer I, float f, you declare all these variables. I is equal to 5. It's going right here. It's statically allocated, so it's predetermined at compile time what's going to be needed, and it can make better use of the data section. This is cleaned up by the stack. What's the stack? The stack is all of the instructions that are in the text, but they're all loaded up. This is a lot of instruction down here. This is like the whole program. Well, how many instructions you're going to load up depends on how your stack is going to be configured. Windows 32-bit stack is a different size than the 64-bit stack. So you want to know what's different. Well, that's the other thing too. People, well, can I install the 32-bit version of this program on the 64-bit system? No. Well, you can. It's not going to run at 64-bit speed. You can't go backwards, so you can't put a 64 on a 32. That's not going to work. Why is that? Because the runtime has a different stack size. You're on a 64 system, it's expecting this size stack. You don't get this size stack, you get a smaller one, that's fine. You're on a small system and you get a big stack, not going to fit. It's too big, not going to fit. You can't stuff a big stack into a small stack allocation. What do I mean by stack? Just like a stack of plates. We're going to take the instructions, it's pre-configured, it's static, so we're going to say there's 5 entries, there's 10 entries. Let's say we're on a 32-bit system, we're going to have 10 stack entries. Loads up 10 instructions from the text, puts them on there, then pops them off. So pushes 10 instructions on, pops 10 instructions off, pushes 10 instructions on, pops 10 instructions off. And then we have another piece of memory that's out over here called a registry system, or registers. They're little pieces of memory, very similar to this, formatted differently. They're smaller. Very small, very expensive form of memory. This is cheap memory. This is your RAM memory, by the way. This is the system RAM that's running these processes. Because we're going to pop all of these instructions, put them on a stack, push them all on a stack, pop the first one off. First one off is going to be integer. Oh, okay, I need an integer. Okay, so I'm going to create an integer. And then the next one's going to be I. Oh, that's my identifier. That's my name and mine. And I'm giving you machine code and C syntax, so keep in mind it doesn't actually sound like this. And then the program counter is going to be 2. We got to 2. Oh, okay. And we're going to store something temporarily in the register. Maybe the name I is going to be stored there or something like that. And then we're going to stop. Because the CPU is going to share its processing with all of the other programs that are running out there. We only get it for like, what, 5 clicks or something like that. 5 ticks, which means 5 instructions if we're going 1 instruction per clock tick. And then we get another program out there that's also stored into memory. That's going to have a different, it's going to go back, where's the program counter at? It's at number 4. Okay, so that's going to go 4, 5, 6. Okay, stop. What's this one? 7, 8, 9, 10. So we're going to simultaneously run 4 different programs until we run out of stack entries that are running, while the user's thinking that all 4 programs are running simultaneously. The CPU is only processing one of them at a time sequentially. So we have this data structure that we're going to put together to keep track of the program counter, where we are in the execution. We have the local, right next to the CPU, we have these things called registers, where we're going to put the memory. We're going to use it because the CPU needs to gather it, because it's going to need to use it when it goes back to this process. And then way back out in memory, we have the cheapest form of memory, which is this RAM that's going to hold all this stuff. It's kind of a timestamp for us, so we can go back to it and revisit it over and over again. That's a large, high-level view of CPU scheduling that works with processes. So all of the concepts of the operating system all work together with the foundational concept of this process that works, and the processes get scheduled by a CPU schedule that keeps track of all the running processes with program counters and stuff, and uses all the memory. So when we get done talking about processes, and we're going to go into CPU scheduling, and then I'm going to talk about memory management, all 3 of those concepts work together. And it's all the base components of what we're calling the operating system from a user's perspective, because that's how our programs are running. So anyway, a few concluding comments on the runtime environment. The stack and the heap grow together. So you make a program in C, and you know, this recursive program, and the recursive program creates extra stack entries. Actually, recursion is a function that calls a function, as an example. So a function that calls another function, calls another function. You keep creating these functions, but you never return from them. You're building up more stack entries. It's the best way of discovering what a stack overflow error is. So you get stack overflow error. Oh, bummer. And then the program crashes usually at that point because you've overflowed the stack. It's overflowed into the heap. Each process has a fixed amount of memory, and you're only going to let the process use this. This is protected memory because this belongs to this process, and only this process can access it. So if you fill up the stack, it grows over into the heap. You get stack overflow error. Or let's say you're a zealous C++ programmer and you just learned about pointers. You're going to go, they knew this and knew that and knew this and knew that, but you never use delete, and you just create a bunch of new. Then you have out-of-memory error. So out-of-memory error does not mean that your computer is out of memory. It means that the program that you were running in here, this ran out of memory. It grew up into the stack, and you just got too much memory in there. Database programs get out of memory all the time, actually. Depends on how they're configured and what you're loading up into memory. Or they start running slower. If your program is running slower, it's because this memory is being swapped around. It has nothing to do with what anything else is running on your computer. So some programs just run slower because they're not allocating and not using memory correctly. Alright, so I want to leave you with that concept. We're not done yet. I have to go over assignment number 1. But I'm going to stop this video for those people who don't like me putting everything into one. So next week is a holiday. It's Memorial Day. We don't have class. Instead, you're supposed to be barbecuing or swimming or golf or something fun activity. That's what the Americans do. So, or barbecue. It's the biggest barbecue holiday. So we're celebrating our memorying the U.S. soldiers or whatever, or foreign soldiers. All right, long story short, we have no class. So don't come here. Go barbecue instead. So I'm going to pick this up in 2 weeks, which is why I don't want to get too far into it, because you're not going to remember anything. So somebody remind me, TA, remind me, I stopped on slide number 4, and we're talking about lecture 3. And we'll pick that up in 2 weeks. So I'm going to stop this part.